Okay, this is a nice number theory question. My first attempt to this question was that I can actually factorize this. I can write it as p into p squared minus 1 is equal to n power 3 into n power 4 minus 1. And then I tried to find if there's some divisibility relation between these. And I did find something. I found out that p cannot divide n, because if p were to divide n, then you would have a factor of p cube over here, but then you only have one power of p in this left hand side, so that wouldn't make sense. So that means that p has to divide this other thing, so p has to divide this n power 4 minus 1. But then what that means is that p should be less than or equal to this guy, right? So p has to be less than or equal to n power 4 minus 1. Clearly that's going to happen. And what other thing I did uh, was that I tried to use something like modulo 4 or something to simplify this, or maybe bring out something which is special to this problem, but it didn't quite work. So I turned to using an inequality, which really helped me out. So you got n cubed into n power 4 minus 1 is equals to p into p squared minus 1. But what we know for sure is that this is going to be less than p cubed into p power 4 minus 1, right? So what that means is that p has to be bigger than n, because these are like increasing functions, as we are in the realm of natural numbers. So these are obviously positive. I mean, these both brackets are positive. At the same time, this function is like increasing. So we know that p has to be bigger than n for this to happening, right? So because p is bigger than n, we can say that p is bigger than or equal to n plus 1. That also kind of tells me that why p cannot divide n. But it like also tells me another thing, that p cannot divide n minus 1 as well, right? And what that means is that if I can write this n power 4 minus 1 like this, I'm going to write this like p squared minus 1 is equals to n cubed, and then this n power 4 minus 1, this is n squared minus 1 into n squared plus 1, which is n cubed into n minus 1 into n plus 1 into n squared plus 1. Okay, so now what we know is that p cannot divide n cubed. At the same time, p cannot divide n minus 1, because p is bigger than or equal to n plus 1. P can in fact divide n plus 1, but that will happen if and only if p were equal to n plus 1. So you have case 1, that p is equal to n plus 1, so then it will divide this thing. If that's not true, I mean p is strictly bigger than n plus 1, that would mean that p has to divide this factor. So case 2 is that p divides n squared plus 1, but that means that n squared plus 1 is bigger than or equal to p. Okay, so that's nice. So let's see what that gives me. So case 1, p is, let's just erase this case 2 for now. So case 1, p is equal to n plus 1. Okay, so maybe we can just substitute p as n plus 1 into this equation, and let's see if something cancels and we get some nice solution. So you will have n plus 1, and this p squared minus 1 can be written as p minus 1 into p plus 1. So n plus 1 minus 1 is just n, and then n plus 1 is n plus 2, which is equal to n cubed into n power 4 minus 1, which I'm going to write like n minus 1 into n plus 1 into n squared plus 1. Cool. You see that this cancels because n is a natural number. Similarly, this cancels because n is a natural number. So that leaves me with n plus 2 is equal to n squared into n minus 1 into n squared plus 1. So that will be n cubed plus n minus n squared and minus 1. Yeah, that looks correct. So this will tell me n plus 2 is equals to n power 5 plus n cubed minus n squared minus n power 4 over there, right? So minus n power 4 and minus n squared, right? I hope I've did it correctly. So it has to be n plus 1 over there, right? So that's correct. let's see what we get from that. We get we get n power 5 minus n power 4 plus n power 3 minus n power 2 minus n, and minus 2 is equal to 0. And then we can use the rational root theorem to use, and I mean integer root theorem would also work. So what we get from that is that n should divide 2. So n can be only one, only two things. It can be 1, so n equals to 1, or n equals to 2. And you can check both of these solutions, and what I found out was like none of them are actually working. So n equals to 5 gives me this is 0, this is 0, and then minus 1 minus 2 is minus 3, which is not 0. So unfortunately that doesn't work. N equals to 2, that gives me n power 5 minus n power 4 is the same thing as n power 4, and then this thing is the same as n squared, and then you have n power 4 would be 2 power 4, which is 16, minus plus plus of n squared, which is 4, and then minus n, which is minus 2 is equal to 0. Well, it's clearly not equal to 0, so which means that this case 1 where p is equal to n plus 1 is completely rubbish. It doesn't work at all. So let's move to case 2. So our case 2 is that p divides n squared plus 1, which means that n squared plus 1 is bigger than or equal to p. Now I was kind of stuck over this problem, I mean the case 2 of this problem, so I was not getting what to do over there. But I actually did figure out how to do this, because you see, because this thing is like an increasing function, I can write it like this: n power 7 minus n power 3 is equals to this function, which is p power 3 minus p power 1. So this is less than or equal to if there was n squared plus 1 in this case, right? So this is less than or equal to n squared plus 1 cubed minus n squared plus 1. And from there it kind of became very clear that this is not going to happen very often, because over here you got a 6th degree polynomial, and over here you got a 7th degree polynomial, right? So it's very clear that the difference is going to be a 7th degree polynomial for sure, which is at max having 7 roots. Let's just see what happens. So first of all, we get n power 3 into n power 4 minus 1 is less than or equal to, well, I can take out n squared plus 1 from that, and I think some things are going to cancel out. So we will have n power 4 plus 2n squared plus 1 minus 1, which is just 0. Okay. First of all, I can cancel out an n squared. So this is going to be n, and this will turn out to be n squared, and this is cancelled, right? And then I can factor out an n squared plus 1 from this guy. So this will be n squared minus 1 into n squared plus 1. So this cancels. So you just have n cubed minus n is less than or equal to n squared plus 2, right? Which means n cubed minus n squared minus n should be like less than or equal to 2. And you can clearly see there are not a lot of values which will actually satisfy this, because as we get to the larger values of n, this inequality will obviously break down. Okay, so first of all, we can see that its derivative is like 3n squared minus 2n minus 1, which clearly looks like it can be factored. So it's like 3n squared minus 3n plus n minus 1, which is n minus 1 into 3n plus 1. Okay, so you can see that because its derivative is positive, as n is a natural number, so you have n minus 1 is either 0 or positive, and this thing is obviously positive, so it's always bigger than or equal to 0. So this is a non-decreasing function. Cool. So well, let's check what happens at n equals to 1. So n equals to 1 gives me that this function actually becomes 1 minus 1 minus 1, which is like negative 1 itself. Okay. Yeah, that looks correct. N equals to 1 gives me this guy. Nice. Oh, and also by the way, actually n equals to 1 doesn't kind of work, because if n were equal to 1, then you have like p cube is equal to p, which means p squared equals to 1. That doesn't work. So that means n equals to 1 is obviously not the place where we want to be looking. So let's look at n equals to 2. So n equals to 2 gives me like this is 8 minus 4 minus 2, which is 4 minus 2, which is 2, which is like, yes, it's actually equal to 2. So what that tells me is that n equals to 2 should be the only solution to this inequality, and thus it could be the only possible solution to this equation as well. So let's check if n equals to 2 actually is the solution. Let's just delete some stuff fast. Okay, so let's check if n equals to 2 is a solution to this equation. So you get p cube minus p is equal to, when you put n equals to 2 in this, you get 8 into, you got 2 power 4, which is 16, and then you got 15 over there. Nice. Okay, so you have like p into p minus 1 into into p plus 1, which is like 3 consecutive integers, one of which is like a prime. Okay, and then 8 into 15, that can be done as 3 into 5 into 8. That's not quite working. Maybe I can write it as 4 into, oh yes, 4 into 5 into 6. So what that means is that p should be 5. This p minus 1 would turn out to be 4. P plus 1 would turn out to be 6. So yeah, that's how it should be going. So p equals to 5. That's the only solution, and like n is equal to 2. So p equals to 5 and n equals to 2 is the only solution. So the sum of all possible values of n plus p, well, that's just 7. So 7 is our answer. Yeah, that's it. That's the problem. Okay, so I will see you in the next video.